this video, we're going to demo using R for doing inference on the difference of two proportions. The data come from 680 responses from the US to a question that appeared on the General Social Survey and 88 responses from Duke students to the same question. Here's the question. Scientists predict that global warming may have big effects on the polar regions within the next 100 years. One of the possible effects is that the northern ice cap may completely melt. Would this bother you a great deal, some, a little, or not at all if it actually happened? In our analysis, we're going to only focus on the answer a great deal and categorize all the other ones as not a great deal, so that the outcome of this variable is going to be binary, either a great deal or not a great deal. The research question we want to tackle is there a difference between the proportions of Duke students and the general public who would be bothered a great deal about the melting of the northern ice cap? Let's start by uploading our data into RStudio. I click on the upload button, locate my data set on my computer, it's a CSV file, and import it here. And in order for me to be able to use these data in my analysis, I also need to then import it in a second step into my workspace. I pick the data set of interest. I want to make sure that heading is selected as yes, so that RStudio realizes that the first row is a header row, and then I click import. There are a total of 768 observations. 680 of them come from the General Social Survey, and the remainder come from Duke students, and we have two variables. One of them is the response, and these could be a great deal or not a great deal. And the other variable is the group, and these could be either US or Duke. So let's take a look at our research question again. We're going to need a hypothesis test to be able to answer this. So let's go ahead and load the inference function in order to be able to do that. Once it's loaded, you're going to be able to see it on your workspace and start analyzing. The data that we're working with is in the ice cap data set, and the name of the variable, the response variable, is the response. These are the responses to the question from the survey, and our grouping variable is basically the variable that indicates where the data come from, either from the general public, indicated as US, or from Duke, and that variable also appears in the ice cap data set and is called group. I'm going to be estimating a proportion here, since these are categorical variables, and the success is defined as responses that said a great deal. Let's start with the hypothesis test, since in order to be able to answer this research question as it's phrased, I would need a hypothesis test. In my hypothesis test, I set the two proportions coming from the general public and the US equal to each other. In other words, their difference would be 0. And my alternative, since the question is asking for a difference, is going to be two-sided. And let's start by using a theoretical method. Let's take a look at the inference function output. I have a response variable that's categorical and an explanatory variable that's categorical as well. So I'm doing inference on two categorical variables, looking at a difference between two proportions where success is defined as the response a great deal. The summary statistics are given in a contingency table, and a visualization of them appear in a mosaic plot on the side. So we have 680 responses from the US. 454 people said they would be bothered a great deal by the melting of the northern ice cap, and 88 responses from Duke, where 56 people said they would be bothered a great deal as well. We can calculate the sample proportions from the two groups and calculate the difference between the two. In this case, the difference is calculated as the proportion of Duke minus proportion of US. We don't really care in which order these groups are handled in our inference function, because our alternative hypothesis is two-sided. If we were looking at an alternative hypothesis that's one-sided, such as greater than or less than, then we would want to make sure that the groups are handled in the order that we would like them to, so that they appeared in the order that we would like them to in our hypotheses. But for the two-sided hypothesis test, it doesn't matter. The null hypothesis says the difference between the true population proportions is 0, and the alternative says that it's not 0. Since we're doing a hypothesis test on proportions, where the null hypothesis sets the difference between them equal to 0. We need to calculate a pooled proportion, which then we use in the calculation for checking our conditions. This pooled proportion is basically calculated as the total responses of a great deal, 510, divided by the total number of observations, 768. That's 0.6841. When we're checking our conditions for the theoretical method, we want to make sure the number of expected successes and failures using both of these groups are greater than 10, and in this case it seems like we meet the condition, so we can proceed with the theoretical method. We have a standard error calculated using the pooled proportion and a test statistic. It's a z-score since we're dealing with proportions, and a corresponding p-value. Since this is a two-sided test, we can see that both tail areas are shaded, and I have a p-value of almost 56%. This is a pretty high p-value, so I would fail to reject the null hypothesis and conclude that the data do not provide evidence of a difference between the proportion of Duke students and the general public who would be bothered a great deal about the melting of the northern ice cap. I think this is the kind of question where one might expect that there wouldn't be a difference between these two groups that we're looking at. We might also want to do a confidence interval to answer this question, and in order to do that, we would simply change the type from HT to CI and get rid of these two arguments where we specify the null value and the alternative hypothesis, since those don't pertain to a confidence interval. Let's run this function again, and the confidence interval suggests that the proportion of Duke students who would be bothered a great deal about the melting of the northern ice cap are 14% lower to 8% higher than the proportion of the general public who would. Since this interval contains 0, it agrees with our hypothesis test from earlier where we failed to reject the null hypothesis. We can also do a confidence interval using a simulation approach. And in this case, we would be constructing a bootstrap interval, so this requires resampling many times, in fact 10,000 times from the original sample, so it might take a while, but the bootstrap interval, while it's not going to give us the exact same values as the theoretical approach, it still indicates the same, such that we wouldn't be rejecting the null hypothesis that sets the two proportions equal to 0, since the difference between the two proportions equal to 0, since 0 is included here. And if I wanted to do a simulation-based hypothesis test, I would need to once again specify my null and alternative and change the type from CI to HT, and this would be a randomization test where the null hypothesis says that these two variables are independent. In other words, that we shouldn't expect a difference between the two proportions, and the alternative hypothesis suggests that we should expect a difference between the two proportions, and we can see that the randomization distribution is centered at 0 as specified by the null hypothesis. In almost 64% of the simulations, we observed a difference at least as large as the one observed in the data. That's quite a huge proportion of the simulations, and hence yields a high p-value, and we would say that we would fail to reject the null hypothesis once again. Once I'm done with my analysis, I want to make sure that all of these results are incorporated in my report, so I want to make sure that the data set is loaded into the report document, and so is the inference function. And then in the inference section, I can present my results of the theoretical and the simulation-based hypothesis tests and the confidence intervals. It may take a second to run this because remember, the simulation approaches take a while to compute since our sample sizes are slightly large. And once the report is generated, we're going to be able to see the same results that we've seen so far, and all we need to do in order to complete the project is to give some introduction, some information about the data, do a little bit of exploratory data analysis, and talk about what the exploratory data analysis suggests in terms of answering the research question at hand, and then present our results for the theoretical as well as the simulation-based approaches, and interpret these results, and also write a brief conclusion, and I'm done with my project. I hope that this video has been useful for using R to do inference on difference of two proportions. Thank you for watching.